Hello everyone, my name is Sharaf, and today I'll be telling you how we can use Metalearning to learn an active learning policy under fairness parity constraints. This is joint work with Daumé and Renkun from Microsoft Research and the University of Maryland. I want to start the presentation by motivating the importance of Metalearning and how it could be used for solving the parity constraint active learning problem. So a lot of motivation for Metalearning comes from being able to learn from previous experiences. Modern machine learning models are really impressive, and what we have seen in the last few years is that these models thrive on learning with large amounts of labeled data sets, where the recipe of success is using large amounts of labeled data in addition to a large model with a strong capacity, leading to impressive performances and broad generalizations. We have seen this over and over again from systems trained on ImageNet to transformer models trained on large image translation corpora to GPT-3 trained for large-scale language modeling. And all of these approaches are under the paradigm of deep supervised learning. But what if we don't have a labeled dataset? What if we are in a domain like translation of low-resource languages, or medical imaging, or personalized translation, or few-shot domain adaptation where we want to deploy a machine learning model for a new domain and we don't have enough training data? All of these are scenarios where we don't have a lot of labeled data for every possible task, every possible situation, or every possible person we want to personalize our system to. So instead of learning every single time from scratch, we should be able to leverage our previous learning experiences to be more efficient when it comes to learning from data. So supervised learning breaks down in the scenarios I just described, but humans are actually really good in these situations. So here on the left, we have a small training dataset for two different scripts, Greek and Futurama, and the task at hand is to classify the image on the right as belonging to which one of these two scripts. It's not difficult for a human to classify the test image on the right as belonging to the Futurama script, although you have probably never seen images for this script before. And the question here is, how can we easily solve this task while state-of-the-art machine learning systems will probably fail given only the 20 samples for each script? And the answer is that we didn't learn from scratch. So while it's possible that we have never seen this particular script before, we have probably seen similar scripts, and we didn't just learn from the 20 training images in the slide. So the core of today's talk is about how we leverage previous experiences via meta-learning to solve some of these challenges. And in particular, we focus on using meta-learning to promote the learning of fair models by solving the parity-constrained active learning task. So now that I have covered a little bit about the motivation, I want to give a quick primer about meta-learning and how it could be used for promoting fairness in learned models. So first, let's look at an example. So this will be similar to the one I have just described in the beginning, where the goal here is to perform a few-shot image classification. So we would like to be able to perform one-shot 5-way image classification, where we are given one image for 5 different classes, and the goal is to classify new examples as being among one of the 5 classes on the left. This is similar to the script classification setting I have shown you before, and here we want to enable a machine to use other training images to solve this few-shot classification problem. In particular, we are going to structure the data from other image classes so that it matches what the system is going to see at test time. So we can sample other 5 classes and structure them into a training set and a testing set. And we can do this for a wide set of other image classes, and they train in neural network so that after it sees a few images on the left, it can effectively make predictions for the images on the right. And we can do this across a number of training classes, learning how to learn from these very small datasets. So that at test time, when the system is given 5 examples from held out classes, it can effectively make predictions about these. So we are effectively trying to match the test time and the training time behavior. So this is what it looks like for image classification, but you can replace the image classification task shown as rows here in this figure with tasks like parity-constrained active learning that we study in this work. Or really any machine learning problem where you want to learn by leveraging your previous learning experiences from other tasks that look similar to what you're interested in. So this is generally how the problem setup looks like in meta-learning. So now let's outline formally what the typical meta-learning problem will look like. So you are probably more familiar with supervised learning. So in supervised learning, we're interested in mapping from an input feature vector x to an output prediction y. And we might do this using a function f parameterized by model parameter theta. And we usually learn the parameter theta using a labeled data set containing pairs of labeled data points x and the corresponding labels y. In meta-learning, however, instead of mapping an input to an output, our goal is to output a learning procedure. So our goal is to take as input a data set and make predictions about new data points from that data set. So the procedure will take as input a training data set, and this data set has k input and output pairs for a k-shot learning problem. And in addition to that data set, we also want to make predictions about new data points. So it will also take a new input point x test. And we are interested in making predictions for the corresponding label to that point, and we call the corresponding label y test. So this is our goal. We want to be able to learn a function f that takes as input a data set and a test point and make predictions about the label for this test point. And the way we might go about solving this, the parameters for this function f, is from a data set of data sets, where every data set will have k data points to simulate a k-shot learning task. And one of the nice things about that view of meta-learning is that it reduces the problem of meta-learning to the problem of finding the function f and optimizing the parameter theta for solving this meta-learning problem. So there has been several approaches for solving meta-learning problem. In this talk, I will focus on optimization-based meta-learning. So this approach is closely related to transfer learning by fine-tuning. So I'll start by describing that. So in the standard transfer learning by fine-tuning approach, we started from pre-trained model. So for image classification tasks, it can be a model trained on ImageNet, and for natural language processing, this can be a BERT model. And we started from this pre-trained model, and then we fine-tune the parameters of the model by running stochastic gradient descent on the training dataset for the new task. But what if the training data is small? So fine-tuning will either overfit because the training data or the updates are not sufficient, and you won't adapt effectively to the new task that we are interested in. So what we want to do in optimization-based meta-learning is to learn better initialization for the parameter theta, better than what we usually get from a pre-trained image or language model. So here is a single fine-tuning step. And what we can do is that we can take this step and then evaluate how well fine-tuning does on a held out data set for this particular task. And then we can optimize for the initialization theta such that this fine-tuning is as successful as possible. And we can do this across all of the tasks that we have in our meta-training data set. So the key idea here is that we learn a parameter vector theta that can easily transfer to new tasks by fine-tuning. So now that I have given some background about how optimization-based meta-learning works, I would like now to show how we can use meta-learning to solve the parity-constrained active learning task. The main research question we try to answer in this work is how can we use meta-learning to learn an active learning policy under a constraint on fairness parity. Let me start by setting up the stage with the definition for the parity-constrained active learning setting that we study in this work. You are probably familiar with the standard active learning setting, where in this setting the learner is presented with a pool of unlabeled training data, U. Our goal is to learn an active learning policy phi that will generate a categorical probability distribution over the pool of unlabeled data points from U. Having generated the probability distribution, we sample capital B points to query for the label 4, and then we train a downstream classifier H by running a learning algorithm A on the B sampled points. And you can think of the learning algorithm A as learning by backpropagation kind of algorithm. So in contrast to the standard active learning setting, we are not only interested in improving the accuracy of the classifier, but we are also interested in making sure that the model is fair with respect to demographic groups. So we evaluate the model on both the accuracy as well as the metrics that measure fairness parity. So for instance, something like demographic disparity or equalized odds. And the main research question is how can we learn the parameters for the policy phi using meta-learning. So our goal is to manage an efficacy versus annotation cost trade-off under a target parity constraint measurement. So we'd like to be able to perform parity-constrained active learning where we are given a pre-trained model and a pool of unlabeled data. And the goal is to select capital B points from this pool to label, and we want to enable a system to use other active learning tasks to solve this parity-constrained active learning problem. And in particular, we are going to structure the pre-existing labeled data that we have to match what the system is going to see at test time. So we can sample other data points from the pre-existing dataset and structure them into a selection pool and a testing dataset. And we can do this for a wide set of simulated active learning tasks and then train a neural network so that after it sees the selection pool on the left, it can effectively select samples to label to maximize the performance under a fairness parity constraint. So that at test time, when given a new pool of unlabeled data, it can effectively select the samples to label. So here what we are effectively trying to match the test time and the training time behavior. So since we are interested in promoting fair active learning strategies, we need a metric for quantifying the fairness criteria we care about. So let's look at a simple example to see how we can define this fairness metric. So let's say we're interested in approving loans for applicants based on their credit score. Here we have two histograms for two groups of people, blue and orange, where solid circle indicates the repayment and empty circles indicate the proportion of people who won't pay. You can think of the blue group as maybe people younger than 60 years old, and we call this the protected group, and the orange group represents people older than 60. So one of the most popular criteria for measuring fairness is demographic disparity. And or demographic parity, where it means that for each group we should approve the same fraction of loans. So if in the orange group we are giving out loans for 60% of the people, then we must also give the people in the blue group 60% of the approved loans. So we use optimization-based meta-learning to solve this problem. So at test time, we start from a pre-trained possibly biased model, and we are interested in debiasing the model by collecting more labeled data from a pool of unlabeled data points U. So to do this, we use a selection policy pi to select the samples to label. And we started from this pre-trained model, and then we fine-tune the parameters of the model by running a stochastic gradient descent on the selected labeled samples. We use optimization-based meta-learning to learn better parameters for the selection policy pi. So this is a single active learning step. And then we evaluate how well active learning does on a held-out data set for this active learning task. And then we optimize for the parameters pi such that active learning strategy is most successful. And we can do this across all of the simulated active learning tasks in the meta-training dataset. And the key idea here is that over simulated active learning tasks, we are interested in learning parameters that lead to minimal loss and satisfy the fairness constraint. So this is how we learn the parameters for the active learning selection policy pi. This is a visual representation for the training procedure, where at training time we assume access to fully labeled datasets that can possibly be biased. And then using the labeled dataset, we simulate parity-constrained active learning setting as we described it before. And crucially, we keep track of the full computational graph generated by the learning algorithm A. And to ensure that the approach is end-to-end differentiable, we use a Gumbel softmax trick to sample from the discrete probability distribution generated by pi. We formulate the parity-constrained active learning task as a bi-level optimization problem and solve it using forward-backward splitting optimization approach that makes sure that we satisfy the fairness parity constraint. We evaluate our approach, we call it Panda for parity-constrained active learning. Here our approach is in red. And we compare our approach to alternative active learning strategy. Here on the figure on the left, we have the demographic disparity versus F-score trade-off. And here on the right, we have the error rate balance versus F-score trade-off. So we are interested in having high F-score while abiding by a low demographic disparity metric. And our approach is the only one that satisfies this criteria. The paper includes more experimental results, and I'll be happy to go over these in more details in the Q&A session. Thank you so much for listening.